Now that you know the basics of mappings, I want to get started with an example of mappings where it will all make sense to you. And that is how you can make sure that withdrawing money from a smart contract is actually money that somebody else put in there. And many people can actually put money in the smart contract. So let's get started with an example before I'm talking too much. And let's just say this is example mapping 2 solidity. Now we can copy over our SPDX license identifier and everything and just call this example mapping withdrawals. Now let me write a simple smart contract and then secure it. The simple smart contract should look very familiar from the contracts that we had before. We have a contract where you can deposit money and then withdraw the money again. So let's just write a function send money, and that is public payable. Doesn't do anything yet. Then a function get balance, public new returns an unsigned integer, and that returns this smart contract's address balance. And then we have a function withdraw all money, and then we just withdraw this to an address. And to.transfer or get balance. Great. If we run this smart contract, let's deploy this, and we put in, let's say, 1 ETH into the smart contract. Then the get balance is 1 ETH, and then we can withdraw the balance, well, from somebody else to somebody else. So now I did deposit with this account, and then I'm switching over to the other one, copy the address, but I don't switch back. And that's the important part. So I can just, as the second one, withdraw all the money to myself. Balance is gone, but now I have almost 1 ETH more minus the gas cost. And that is the exact problem where we would need some sort of extra data structure to make sure that this doesn't happen, and so on and so forth. But the question is, can we make this kind of like inherently secure by tracking who deposited what and just let people withdraw as much as they deposited before? And there's actually a way, and there's an elegant way instead of dozens of different variables. And the elegant way is to use a mapping that tracks the balances received. So let's improve this smart contract. Let's say we have a mapping that maps addresses to unsigned integers, and that is maybe called balance received. And then we need to track this somehow. Well, in send money, we are going to increase the balance received from message sender gets incremented by the message.value. So the plus equals means balance received message sender is balance received message sender plus message value. So whatever is in there already stored gets incremented by message value. If you've never seen that before, that is something that you will see quite a bit and is basics. Now in withdraw all money, instead of letting the user withdraw the amount of money that is in total in the smart contract, we will just let him withdraw the amount of money that was sent by this user to send money. So what he can withdraw is what is basically in here. And it's not quite there yet. Let me just write the more or less pseudocode in there. So what he can withdraw is what is stored in balance received message sender. But obviously we also need to reduce this. And we could do this over here. We could easily say like transfer to that address the balance received, and then balance received dot message dot sender equals 0. That would be a valid thing, but here we would open it up to a sort of re-entrancy attack, and it's not really possible with the transfer function because it only gives you a minimum amount of gas. But in general, this is called the checks, effects, interactions pattern. So what you should do, what you should not do is what is here. And what you should do is first check if the user has enough balance. But we don't really do that yet because we will see in the next few lectures about exceptions and require statements and so on how this works. And we can improve it there. But then we are going to apply the effect and then have the interaction to an external address. So instead of first sending out and then applying the 0, we first have to apply the 0 and then send it out, because this address over here could call back into that smart contract. And if it is possible to do that, then it could actually withdraw again before it gets set to 0. And that is the problem with the re-entrancy attacks that happened on the DAO, for example, which was one of the first voting and crowdfunding smart contracts that got hacked, that led to the split between Ethereum and Ethereum Classic. Now, a small thing can have a huge impact. So how are we going to do that? First of all, we are going to cache our value, balance to send out is balance received message sender. Then we set balance received message sender to 0. And then we are going to send out the balance to send out. And this way, even if this smart contract or whatever is running here would be, for whatever reason, be able to call back this function again, at that point, the balance received would already be 0. Now, the good thing is it's inherently secure. So you cannot withdraw more money from this smart contract than you actually initially put in. So let's give this a try. Let me just close this over here. We are going to deploy the smart contract with the first address in our address list. And I'm going to send 1 ETH to the smart contract. And now in the smart contract is 1 ETH. And I'm going to the second address and I'm going to deploy, I'm going to get 1 ETH into the smart contract. Now we have 2 ETH in the smart contract. The thing is, our address over here, this one, if I paste the address into the parameter for balance received, then it only sent 1 ETH. So even if I say I want to withdraw all the money to myself, all I can do is withdraw the money that I sent to the smart contract back to somebody else. So I kind of like put it in escrow. I have no access to the other funds that the other person sent. So even if both or all parties are having access to the same smart contract and can run the same functions, inherently by the data structure used by the smart contract, only one can interact with the data it has actually access to. Even though you can track and see everything, you cannot modify it. And that is very important to understand this difference, especially if you want to build something like a wallet, an escrow smart contract, a voting smart contract, or any kind of smart contract where more than one party can interact with each other, like a token. A token is nothing else than increasing balance on the one side and decreasing it on the other side. That is how an ERC20 token works, and you will see this later on. Now, enough of that. And we are going on with structs, which are bringing a little bit more complexity into the game, but making it much nicer to work with smart contracts with a lot of data.